Welcome to the electronics class for December the 15th. I have looked over your scores on the homework assignment from last night, and they look very good. I'm really pleased with how many of you guys got 10s. Several of you got 8 out of 10. And I noticed that some of those of you that have 8 out of 10, for the most part, you only gave it one shot. You know you're allowed 2 shots on these. So those of you that got 10, I see that most of you got 10 on it the first time around, which is really encouraging. But even if it took you 2 tries to get a 10, that's okay. That's fine. So those of you that got 8s, you should have gone back and tried it a second time. You could have turned that 8 into a 10, but it's too late now. And there are a few of you that didn't do it at all. Guys, what can I say? I don't know what I'm going to do with you guys. But that's only very few. Most of you did really, really well. Okay, so what that tells me is that you are understanding how to analyze forces and structures, and that's good. Today, the assignment that I'm going to give you, I'm going to let you cheat. I'm going to show you a spreadsheet where the spreadsheet does the calculations for you. And what you need to do is you need to answer some questions we'll talk about in just a minute. But the calculations, those will all be done for you. And that, in fact, is the way that things generally work. Not always, but in a great many cases out in industry, when engineers are designing something, there's usually some software that does all of the boring calculations for you. But it's really important that you know how the calculations work. And there are going to be some instances where there isn't software that does it for you. Okay, so let's just take a minute here and do a bit of quick review. Before I do that, let's open this up. Okay. All right, so I'm going to share my screen. And so the picture that you should be seeing on your screen right now is a very familiar one. This shows you the structure that we were using in our homework assignment. And there's a couple things about this that I want to make sure that I point out. Okay. So in the homework last night, we had a triangle where this angle and this angle were not the same. So that means that the length of this side and the length of this side were not the same. And in real life, you know, that is the way that the bridges are usually designed, is that these guys are not necessarily the same. But for tonight's homework, I'm going to make it a little bit easier. Tonight, I'm going to give you a bridge that looks like this, where the triangles that you see here are going to be isosceles triangles. So what I mean by that is that this side and this side are going to be the same length, not because they have to be, but just because it simplifies what we're going to do tonight. Well, there's enough complexity in what we're going to do tonight that I didn't want to add that level of it. So I'm simplifying it. So if those two sides are the same, that means these two angles are the same. Not because bridges have to be designed that way, but just because it simplifies things. Okay, and then there's another thing that we're going to do in tonight's homework is we're going to add a load, and the load is going to be located in the center of the bridge. Remember a while back, you guys had a homework assignment where you had to talk about dead load versus live load? Okay, so the dead load is the weight of the bridge itself. And then the live load is something that that is on the bridge. So you have its weight in addition, okay? And now I've got it in tonight's homework that the live load is going to be right in the center of the bridge. So everything's nice and symmetrical, but in the real world, that won't be the case. So this picture that you see here is a little bit more representative of what a real world bridge would look like. And you can see that the live load here, which is Homer, is not necessarily in the center. He could be over here, he could be over here. In fact, in what's really going to happen is he's going to walk across. And so the forces on the bridge are going to change as he walks across. As long as he is closer to the left side than he is on the right side, you can see that the support force that's holding the bridge up on the left side is greater than the right side. Now, when he gets to the middle part, then the left and right support forces will be the same. And then as he keeps walking and gets over here, then the right force will be greater. So this is a complexity that you need to deal with in real life. When you're designing bridges, you need to account not just for the dead load, but you also have to account for the fact that there's going to be a live load walking around there. And that complicates things. Okay. But again, for tonight's exercise, I'm not going to do that. I'm going to assume that the whatever is the, whoops, sorry, wrong. I got to remember to turn on annotation before I touch the screen here. So this is the thing that's going to be our live load. So I'm going to assume that it is exactly in the center. And we're not going to worry about the fact that it had to walk in from here and walk out from here. We're just not going to worry about that, at least not for tonight. Because for tonight, I wanted to keep things as simple, or I wanted to keep things relatively simple, because we've got enough of a complexity in tonight's bridge here. Okay, so here's the deal. In the bridge that you're going to do for tonight's homework, okay, you have a choice on what to make each of these pieces out of. Now, each of these pieces, we have a special name for it. We're going to call them a member, which is what civil engineers usually call them. So we've got these different members here. And now, because everything is symmetric, then this member here is going to be exactly identical to this one, and the forces in that member are going to be the same. Same with this. This member here and that member there are going to be exactly symmetric. This member here and this member here are going to be exactly symmetric. Now, if the live load here is over on this side, okay, then the symmetry is ruined. But for tonight's exercise, let's just assume that everything's nice and symmetrical. Okay, so you see we've made some simplifying assumptions. Okay, now your job for tonight's homework has several parts to it. First thing you need to decide is how tall do you want to make the bridge? Hopefully you guys remember that when we did the analysis here, we did a bridge where the bridge was really quite short. Okay, so what you see in black there, that was the bridge that we designed. But do you remember what the problem was when we made the bridge really short like that? Can somebody unmute yourself and tell me what was the problem that we encountered when we made the bridge really short? What happened to the forces on the members in that bridge?
They were really high.
Yeah, they were really high. And especially this member right here, which is that guy right there, when we made that bridge really, really short, the force in that member there was so incredibly high that that bridge probably would not have been able to withstand that force. And so the bridge would have collapsed for sure. So the taller you make the bridge, the less the forces are. And so that's good, right? But the bad thing is if you make the bridge really tall, then you're going to have to buy long pieces rather than short pieces. So it's going to cost you more money to make the bridge. So this is something that engineers worry a lot about, is how can you minimize the cost of the bridge? Because what we're going to assume for tonight's homework is that a customer has come to us and they've said, hey, I want you to submit a bid for building this bridge. But I do need to warn you that I'm also talking to a whole bunch of other companies as well. And so all of these companies are all going to submit a bid for this bridge that I want built. Whichever company can submit the lowest bid that does the job reliably without the bridge collapsing, they're going to get the money. So your job is to design me a bridge, and I'm going to look at the cost, but I'm also going to look at your design, and I'm going to look at the forces. If the design that you've given me for your bridge is not going to be strong enough where the bridge is going to collapse, then obviously I can't give you the job. So you need to design me a bridge that can withstand that's made out of materials that can withstand all the forces that are going to be exerted. And assuming that everybody's bridges are all going to be structurally sound, then I'm going to pick whichever bridge is the least expensive one, and then that company is going to get the job. Okay. But if you give me a cheap bridge that's not going to be structurally sound, well, then I'm not going to give you the job. All right. So what we have here is we have a couple different choices of materials that we can use. So you can see I've got in 3 different categories here. I've got slats, I've got I-beams, and I've got cables. So what do we mean when we talk about slats, I-beams, and cables? Well, do you guys remember the reading assignment that I gave you out of the textbook a while back, where you had to, I had to read you through there? Okay, so hopefully you remember when you read the book there that there are different shapes that bridge members can be made out of. So what you see on the left here is called an I-beam for an obvious reason. If you look at a cross section, it looks like the capital I. Whereas on the right here, this is what's called a slat. So basically it's the center part of the I-beam without these upper and lower flanges there. Okay, so a slat is kind of like this popsicle stick. Okay, so this popsicle stick is basically a slat. Okay, and so if you were to take this popsicle stick, if you pull it on either end so that the popsicle stick is under tension, it can withstand force pretty well. Okay, it can withstand a lot of tension force. If you squeeze the popsicle stick so that it's under compression, okay, it can withstand force pretty well, but there is a point where it will buckle. Okay, if you put too much compression force on it, then the thing will lift up like this, and then it'll break. And we have a word for that type of failure. That's called buckling. So anything that's in the form of a slat, it's going to be pretty good. It's going to be quite good at withstanding tension forces. Not so good at withstanding compression. I mean, it can do some compression, but not too much. So what can you do to make it stronger so it withstands compression better? Well, take a slat and put another slat on top of it and another slat on the bottom of it. And it's hard for me to hold it like that, but if I go back here, so basically an I-beam, okay? So an I-beam is made up of 3 slats. So you've got the main part of it here, and then you've got a slat that's welded on the top there, and you've got a slat that's welded on the bottom there. And what that does is that makes it so that this member can now withstand compression forces a whole lot better. If I were to take this exact same popsicle stick and I weld a top piece on it and I weld a bottom piece on it, okay, now what you'll find is that that thing can withstand compression forces much, much better. And since it's also got these additional pieces on it, that's also going to help it to withstand tension forces better too. But the main thing, the really important thing, is that it's going to withstand compression forces a whole lot better. Okay, now, what about a cable? Okay, so let's say I've got a cable here, right? So if I pull on the cable, it can withstand tension forces really well. Okay, if I put it under compression, well, then can't do anything. The cables are completely useless if the forces that they're experiencing are compression forces. They're no good at all for that. But for tension forces, cables work pretty well. Okay, so what you need to do in tonight's assignment is you need to look at this bridge that we're going to design, and you need to decide for each of the different members, do you want to make them out of an I-beam? Do you want to make them out of a cable, or do you want to make them out of a slat? So any piece that is going to be under compression, then obviously slats are not even in the running for that. Okay, so the first thing that we need to do is we need to identify which forces are going to be under, or which members are going to be under tension and which ones are going to be under compression. Okay, so in your homework last night, you had a bridge that was very, very similar to what you see here. And hopefully you remember what was what. So this force member number 2, let's see, hang on a sec. What, for some reason, there we go. For some reason, it didn't want to let me write on the screen. So member number 2 is under compression, and member number 4 is under compression. Member number 3 is under tension, and member number 1 is under tension. Okay, so, and then because everything is symmetric, that means this guy's also under compression, this guy's also under tension, this guy's also under tension. All right, so knowing that, we know that for member number 3 here, because it's under tension, we could use a cable there if we wanted, but for member number 2, there's no way. Cannot use a cable for that. Now, let's look at member number 3 here. Cables. Well, you look at the cost of a cable compared to the cost of an I-beam or the cost of a slat. Cables are generally cheaper. You know, they're not a whole lot cheaper than slats are, but you know, they for a given diameter they are. So let's say that we've got a cable that's 1 inch diameter, and compare that with the slat that's 1 inch by 4 inches. Okay, you see that 1 inch cable costs you $5, where the slat there is going to cost you $20. And now, so the cable is round with a 1 inch diameter. The slat is 1 inch by 4 inches. Okay, so so it's not surprising that the cable is going to be cheaper. Now, how about the forces there? So a cable can withstand 3,000 pounds of force, depending on what the cable is made out of. Now this is something that I need to point out here. Okay, so it's really important to know, is the cable made out of aluminum? Is it made out of wrought iron? Is it made out of stainless steel? And there are different grades of stainless steel. There's called stainless steel 16. There's different grades of stainless steel. Okay, so now I am assuming that we've got some imaginary metal made that's called unobtainium, which is a science fiction reference some of you may recognize. Okay, so what I'm assuming is that if we have a 1 inch cable made out of unobtainium, it can withstand 3,000 pounds of tension force, whereas a slat can withstand 5,000 pounds. So I might be willing to pay the extra money to get the slat if I need that extra tension. But if I don't really need it, I'd be better off using a cable. But this is only for member number 3. Obviously, for member number 2, cables are not even an option. So for member number 2, we can decide, well, slats do withstand some compression, but not very well. I mean, compare a slat with an I-beam. So if we've got a 1 by 4 inch slat, it can withstand 100 pounds of compression, whereas a 4 by 4 I-beam can withstand 3,000. So I mean, there's like no comparison there, right? So clearly, if an object is under compression, an I-beam is going to be stronger than a slat. And now the problem is that an I-beam is going to be more expensive than a slat. Okay, so are we willing to pay the extra money to get I-beams, or are we willing to get slats? You know, depending on what the forces are, you know, maybe we can get by with a slat, and slats are certainly less expensive. Okay, so this is your job, is to figure this out. Now, if I asked you to do all the calculations by hand, this would be a mess, because the first thing you need to decide is, how tall are you going to make your bridge? So if you make your bridge relatively short, okay, then you're gonna have to figure out, first off, okay, how much is the bridge going to weigh? Because a short bridge is going to weigh less than a tall bridge, right? And so what you'd have to do is you have to say, okay, well, let's suppose that I make my bridge out of these things here. And so then you're going to have to figure out, okay, how much is the bridge going to weigh? And then that determines what the forces are going to be on the other side here, because the more the bridge weighs, the more this force is going to be. And so you'd have to calculate how much the bridge weighs. And then you'd have to calculate what these angles are going to be. And then when you add in all the forces, then you can calculate how much force is in each of the members here. And that's going to be a lot of work to do that. And then what you're going to have to do is you're going to say, okay, now let's compare that with this taller bridge. Now, if I make the taller bridge, then the bridge is going to weigh more. So that's going to change this force. And the angles are going to be different. So that's going to change that. So you can see if I ask you to do all this calculation without giving you some sort of software that helps you out, that would be a very, very difficult task. Now, I am mean, but I'm not that mean. So what I've done to help you out here is I have given you a spreadsheet that's going to do all of the calculations for you. So let's look on Canvas here. All right, so you should all be seeing my Canvas page right now. So let's click on assignments, quizzes, and tests, or click on modules. They take you the same thing here. So if you look down, so here is the assignment, which is due next time we meet, December the 17th. Optimizing bridge design using a pre-made spreadsheet. Okay, so I click on there. And so here is a copy of the bridge that you see with all the parts labeled. Here is a copy of the available materials that we can choose to make each of the members out of. And this is the exact same sheet that I gave you before. So it tells you what the different sizes are and what is the maximum compression, maximum tension, the weight per foot, and the cost per foot. Okay, but the important thing is that the spreadsheet is going to do all of the gruesome calculations for you. If you click on this link right here, then it will open up a Google spreadsheet. Okay, and it takes a few seconds for the picture of the bridge to load, so be patient here. Sometimes it takes a little longer than others. Okay, there we go. All right, so it is fully loaded. Okay, now, because I am the creator of this spreadsheet, then I can change anything on here. So I can go in here and I can type in numbers and things anywhere that I want, okay? But I don't want you guys to accidentally mess up my spreadsheet, okay? So what I'm going to do is I'm going to log out of my account here. Okay, so let me come down here. So I'm going to sign out of my account. And by the way, if I am trusting that all of you guys have a Google account. If you don't have a Google account, well, actually, you can do some things. You just won't be able to save your work. Okay, so please, if you don't already have a Google account, get a Google account. Okay, so now watch the difference here. Now that I'm logged out of my Google account, so now when I click on this, what I see is the same thing that you guys will see when you click on it. Okay, so let's wait a little while here. And you see, even though I'm logged out of the account, it still opens up the spreadsheet for me. Okay, there we go. All right, so it's now fully in. Okay, now notice there's a little thing here that's different from what was before. Let me turn on annotation here so that I can highlight it for you. Okay, so what we've done is when you open up my spreadsheet, because you are not the creator of the spreadsheet, I've got it set so that you cannot make any changes to the spreadsheet. All you can do is view the spreadsheet. So if you come down here and you click somewhere to try and type something into the spreadsheet, it won't let you. And if you click on here to try and change the numbers, it won't let you. You can only view it. So you might say, well, what good is that? Well, what you can do is you can come over here to where file, and then you can make a copy of the spreadsheet. Okay. Now right now it's not allowing me to do that because I'm not logged into my Google account. But if you guys were logged into your Google account when you open this, then it will let you make a copy of the spreadsheet. Or you can also download the spreadsheet too. And you might want to do that. If you have Excel on your computer, you can download the spreadsheet as an Excel spreadsheet. But I think the best thing to do is just make a copy of it. Okay. So so now let me log in again. And tell you what I'll do is I'll log in as a different one of my mini accounts. Okay. So the account that I'm logged into right now is not the same account that I used when I created the spreadsheet. Okay, so now what I can do is when I click on file, now you'll see that make a copy is an option for me. Okay, so that is what I want you guys to do. I want you to make a copy, and you can call it whatever you want. I'm just going to go with the default suggested name here, but you can make it whatever you want. It's going to save the copy on your Google Drive, which I hope you all have a Google Drive. Okay, give it a second to do it. Okay, now we're in business. Right now we can actually start doing something with the spreadsheet. All right, so the cells that are in yellow, those are the cells that I want you to change. Please don't change anything else. If you accidentally click over here and accidentally change the numbers here, that's going to mess everything up. So please be very careful not to change anything except for the cells that are in yellow. Now, if you do accidentally mess something up, don't worry. You can just go back to the back to here and then just download another copy of the sheet. That it's not like it's a fatal mistake. Okay, so the first thing that you need to decide is how long do you want members 2 and 3 to be? So you'll notice I've got a little note here that says that they have to be at least greater than 12.5. And the reason for that is this distance right here is 25. So you can see if I make members 2 and 3, let's say that I make each one of them be about 13 feet long, then that means my bridge is going to be super, super short. If I make them be exactly 12.5, then that means my bridge is going to have 0 height. That means that member 2 is going to be lying perfectly flat. Member 3 is also going to be lying perfectly flat. And that's not going to work too well. In fact, let's find out what happens. Let's just have some fun with this. Let's make members 2 and 3 be the smallest possible, which is going to be 12.5. So I'm going to type in 12.5. When I hit enter, I don't notice any problems immediately, but when you look down here, you'll see we've run into a huge problem here. The spreadsheet is automatically calculating everything for you. The spreadsheet calculates what the height of the bridge is going to be. The spreadsheet calculates what the different angles are going to be, and all of these numbers depend on what number you put there. And the spreadsheet is going to calculate what the forces are in each of the members. And if you have a 0 height bridge, the forces are infinite. And so that can't work. All right, so let's say, well, all right, so 12.5 obviously doesn't work. Let's make it be 13. Okay, so what that means now is that member 2 is 13 feet long. Member 3 is also 13 feet long. So you can see here the height of my bridge is now only 3 feet tall, which is a really, really short bridge. You can see the angle A here, it works out with the number that I've chosen. Angle A works out to be 16 degrees, and angle C is also 16. And angle B is 148. Okay, but what about the forces in the bridge here? Okay, so again, here the sheet has done all of the calculations for us. It figured out for each member here how long each of the members has to be, and it knows how much it weighs per foot. So it calculates what the total weight of the bridge is. Okay, and then it calculates the forces. And so look at the forces in the bridge here. If I have a bridge that's only 3.8 feet tall, the forces in each member here. So this is the force in member one, this is the force in member two, member three, member four. Those forces are huge. And if you look at the numbers over here, you'll find out there's no way that this is going to work. These numbers here are so big that this bridge is going to collapse. So having a 13-foot bridge here is not going to work. Even if I go with the very, very biggest one, let's say I go with option number 7. That's the I-beam that is 10 inches by 10 inches. That is a really big, really expensive I-beam. But even with that I-beam, the maximum tension force that it can withstand is 17,000 pounds. And you can see here that the force in there is going to be 25,000 pounds there, 26,000 pounds there. So clearly that's not going to work. And also in compression, it's even worse. Member number 4, which is the guy up at the very top, he's going to have over 51,000 pounds of force, of compression force in him. And even if I go with option number 7, which is the strongest, most expensive choice, that's just not going to work. This bridge is going to fall down. Okay, so putting in 13 as my number right here, that's just not going to work. Okay, well, let's play with a couple other numbers then. How about, let's go on the opposite end of the spectrum. Let's make this number be really, really big. Let's make it be like, say, oh, I don't know, maybe let's have it be 40 feet. Okay. All right. So that means my bridge now, if I choose 40 feet for members, for lengths of members 2 and 3, my bridge now is going to be 38 feet tall. Wow, that's a really tall bridge. But look at the forces. The forces in the members are now a whole lot smaller. So very manageable. So I now have a lot of choices that I can use. I don't have to go with the most expensive I-beam as my choice. I can go with smaller things. Okay, so let's go through and let's look at it. So member number 1 is in tension. Oh, and by the way, one thing I forgot to tell you. If you scroll up here, you'll see I want member number 1 to be an I-beam, because member number 1 is the one that people are going to be walking on, okay, or maybe trucks are going to be driving, and I need something that's really, really stiff because I don't want it to sag when people walk on it. So one of the requirements is that member number 1 must be an I-beam. You have no choice on that. The other choices, the other guys, I'll leave it up to you, whatever they want to be. But member number 1 must be an I-beam. That is one of the requirements of the functional specification. Okay, so if we come down here, if we click on this little pull down arrow, you'll see that the available options pop up. And you'll see I've made the spreadsheet so that the available options are all I-beams. You cannot choose anything that's not an I-beam for member number 1, right? So the smaller the number here, the less expensive it's going to be. So if I choose member number 4, if I choose option number 4 for member 1, okay, so you'll see that oops, sorry. Okay, you'll see that it recalculates everything. So you'll see that the force has changed because the weight of the bridge has changed. Look what happens if let's suppose that